Fancy meat computers. How's everybody doing today? Hope everybody's doing okay. So, how did the test go? Did you, by poll results, at the moment, we have, about 30% of the class think it went good. About 10% of the class did not like the way that it went. About 6% of the class were like confused and alarmed. And 65% think that it was a brain hammer. Alright, let's see here. That's a lot of feedback. Alright. Test was okay, then I came across 3C. Yeah. Yeah. 3C was, like, I knew that was a hard question, right? Like, that was, like, 3C was the original idea, and then 3A and B were like, let me see if I can break this thing up so that, you know, it's not all one clump, you know? And maybe give some part marks if you can do some of the stuff required to do 3C. But question 1 and question 2 were generally okay. Yeah. Yeah, 3C, like David says, wasn't too bad once I figured out what it was asking me to do, but a big struggle in that was figuring out what it was asking. Yeah, it was, it's kind of like, yeah, I get that. It's like a multi-layered thing, right? It's like you have a thing, you're supposed to produce a thing which has a few different properties, right? But yeah, let's see. 1 and 2 were pretty easy, to be honest. Q1 took me a while to figure out how to implement a solution, but after that it went well. Yeah, okay. Good. All right. Well, you know, we'll see how the grades come out. Took me forever to figure out what to do with the double pointers. Yes, that was kind of the point, so to speak. Like, while it was a difficult question, I think it tested pointers really, really well. You know, like, you have to know pointers to be able to do that question. When do you think we'll get the grades? Probably in about a week, I should think. Chev has to get all of the test cases that were written by Jala together if she did write them. I'm not sure what the state of the test cases are. At any rate, it usually takes him about a week to get everything together after submission, so that was kind of the point. Bop, 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 bop. So yeah, it should be, like, I would expect certainly the grades minimally by Monday next week. But, you know, we'll see how it goes. How do part marks work? Good question, Ryan. So, when we grade the tests, we're using a bunch of test cases, right? Some of those test cases will be easy, some of those test cases will be hard. The test cases, like, basically your mark for that question is proportional to the proportion of test cases that you pass, right? So, if your solution only works for, like, you know, like, if your solution to question 3C only works when, you know, when the subsequences are at least like 5 long, I don't know why that would be in code, but imagine it was the case, then like a test case that tests that long a sequence would work, but one that didn't test that long a sequence wouldn't work. So, you know, it's like that kind of thing. So yeah, things are going to be marked pretty much in the same manner as they have been so far. But yeah, don't worry, there will be part marks available. Good. All right. Sounds good. So, let's continue with our lecture material, shall we? So, we're going to talk about bitwise operators. Are the test cases we are provided incorporated into that? No, not generally. So I'll speak just a little bit more about test cases before we move on to the actual lecture material. So we have to give you different, like we have to test you against different test cases than were provided in the test, for the simple reason that it's trivial for a program to satisfy any particular test case, right? The way that would work is if you had like a bad actor, and I'm not saying there are any in this class, but you know, if there was one, then this is how they would operate. All you have to do to pass test cases that you know exist is to write an if statement that checks for that input and then produces the expected output, and bing, bang, boom, you are finished. That's it. You've won the test, right? So the thing that we have to do then is we have to test you against test cases that you haven't seen before, because that way you can't just write a simple little if statement and not actually have to do the program. So yeah, the test cases provided will be different, or the test cases we use will be different from the ones provided by the exam, or by the test. So, yeah. 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 Unfortunately, I haven't had time to, like, install a bracket on the wall or anything for my poor webcam. So it's just really just duct taped, like actually literally duct taped. And I was doing some pressure canning over the weekend. I made myself some broth. I made a batch of chicken stock, and that just steamed up the house and caused my tape to fail somewhat. So I was just retaping. I really should use better tape than Scotch tape, but you know. If you pressure can broth, then you can keep it. You can store it at room temperature. It doesn't need to be refrigerated, and it keeps for up to 2 years. Which is a pretty good deal. Anyway, so Bitwise. We're going to talk about Bitwise operators. So, Bitwise operators will become very important when you start working with embedded systems. So, let's review them. This kind of slightly assumes that, like, it's framed as if you should already have heard of Bitwise operators, but, like, we're going to go through them in detail. So, you've got Bitwise AND, OR, XOR, left shift, right shift, and bitwise complement. Bitwise means by the bit, where individual bits are the values under consideration. So, if you think about a bitwise operation as a comparing of the individual bits in the the sequence of bits that composes like an integer, for example, then you're on the right track. So let's talk about AND. Bitwise AND may be thought of as the application of a logical AND gate to each of the bits in the two operands sequentially. Common applications in C include what is called bitmasking. So, hopefully you guys have taken a little bit of electronics, so you know what an AND gate is and does, right? You just literally take the signals and you AND them together, and that gives you the result. So if X was 00110011, and if Y was 01010101, you can see that X bitwise AND Y is 00010001. That's pretty easy to understand. But I'll explain what bitmasking is for a moment. So sometimes it might be the case that you want to take, let's say you had a 16-bit integer, and you wanted just the lower half of it, right? You didn't care what the upper half was doing, you just cared about the lower half. One way to extract the lower half of that integer is to perform a bitwise AND operation with it, and set to 1 in the thing you're ANDing it with all of those bits that you want to be kept. So, that's what we call bitmasking, because it's like, you know how like you can apply a mask in Photoshop and it like just allows certain parts of the photo through? That's essentially what we're talking about here. So yeah, that's AND. We also have bitwise OR. OR is applied in the same manner, but uses a logical OR operation. So, oh, that's a typo right there. Whoops. Can I fix that? Oh, I've got the wrong PDF. Well, that would do it. There we go. So, bitwise is vertical bar, right? Whenever X and Y, whenever X or Y is at a 1, then the result will be a 1. So, taking the same X and Y that we were talking about before, you can see you only get a 0 in the bitwise OR of these two things if both of them are 0 to begin with. So this should be, again, this should be relatively straightforward. XOR is a little bit tricky. People, oh my god. Thank you. There we go. So, the caret character means exclusive OR. Exclusive OR, or XOR, outputs 1 if the inputs are dissimilar. Common applications include bit toggling and arithmetic addition. So I'm showing you circuits here, not because I expect you to memorize them or anything. I'm trying to impress upon your brain that these are very simple operations, right? So one might ask, what is the purpose? Like, why Bitwise? Why is Bitwise so interesting? The operations are very fast. A bitwise operation can be calculated in a fraction of the time of any other operation because it has a lot less circuitry to propagate the signal through. Now, this might be, one might make the argument that, since a CPU is set at a fixed... I'm going to sneeze. Ugh. Pardon me. Sorry. I'm just falling apart today. Pardon me. One might say that because a CPU is, thank you. For XOR, is that the caret character? Yes, it is the caret character. That's C-A-R-E-T. So, there. So, what was I talking about? Lost my train of thought. CPUs. Clock cycles. Yes! So, like, in a CPU, since the clock cycle is sort of, a fixed duration of time, and it's enough time for any operation to be fully processed. The fact that bitwise operations are faster and simpler doesn't really gain you anything. But if you were designing custom purpose hardware in order to, basically if you had custom purpose hardware that used exclusively bitwise operations, you'd be able to clock it faster because the actual operations take less time for the signal propagation versus something like addition, which requires signal propagation. Like, you have to start at bit 0 and propagate a signal all the way through to, bit 64 or something, which takes a lot longer than being able to propagate that signal simultaneously through every single bit in the integer simultaneously. So, and that's sort of the essence of bitwise. Unlike something like addition, each bit has no effect on its neighbors, at least with respect to AND, OR, and XOR. As we'll see with shifts, that's a little bit different, but, whatever. But anyway, so XOR, common applications of XOR include bit toggling. So if you XOR with 1, you'll turn a 1 into a 0 and a 0 into a 1. You'll find, like, eventually you'll have a lab where you have to make an LED flash at a certain interval on a microcontroller, I think, probably. Like, that's the sort of thing an embedded systems person would have to do as, like, their first lab, in my opinion, at least. So, one way you can do that is to, like, set up this big if statement to handle it. The other way is to just, have a single assignment statement which toggles the bit using XOR. So, basically, it's AND with the case of one XOR 1 excluded. So, left shift. The left shift operation moves the bit values of the number x by a number of bits y to the left. We consider left to be toward larger place values in big endian systems, which is most of them. Do you guys know why they call it big endian and little endian? Have you heard the story about big versus little endian? So, from a pragmatic standpoint, this is precisely the same as multiplication by 2 to the power of y, because, of course, we are in the binary system. So, essentially, what happens is you have some number. This represents left shift by 1. So, you take every value, put it one place value higher, whatever's at the end gets deleted, and you backfill with zeros. And that's what left shift does. No! Aha! Okay, I will tell my story. So, as near as I can figure out, the term big and little endian derives from the book, the popular book of the 1700s, Gulliver's Travels. During his travels, the first island that Gulliver encounters is one where the people living there are only about yay high, and so he's an enormous giant. And in this sort of group of islands, there are 2 civilizations of these miniature people, which he calls the Lilliputians. You know, if you've ever seen like that famous illustration of a guy like roped down by tiny people, that's Gulliver's Travels. When you say that, all I think about is Jack Black. Well, yeah, Jack Black did an adaptation of Gulliver's Travels, but just the part with the Lilliputians. In fact, Gulliver's Travels goes on to describe several other societies. Some of them, low-key, pretty racist. But, you know, it's like 300 years ago, so, you know, it's still worth reading, even if you can read past that sort of thing. But, so you have the 2 kingdoms, and they've been at war with each other for a century. And the reason they're at war with each other is because one society is big endian, and the other society is little endian. And so what it means to be big endian in this story is it means when you are cracking an egg for your breakfast, you crack it at the big end. And with little endian, you crack the egg at the little end. And of course, you know, it's like a satire on war because it's such a trivial difference, but, you know. At any rate, so yeah, so that's where the origin of the terms big and little endian come from. Why would we want to shift something to the left anyway, especially if it's going to delete the first bit? Imagine you have a series of LEDs, all right? And you want to do like a marquee of like you know what a marquee is? It's like a light that travels. It looks like the light is traveling, but it's just sequentially the lights are turning on. You would do that, like, the easiest way to do that would be with a left shift, because, like, those LEDs will be wired. Like, if all of those LEDs are wired to, like, one register, then performing left shift on that register will move that light through the LEDs. But I crack an egg in the middle. Exactly. Exactly. In fact, I would argue it's correct to crack your egg in the middle. But then again, I guess that would make me a mid-endian, eh? We'll both be mid-endians together. We'll go found our own civilization in a chain of islands somewhere in the Pacific. So we have left shift. Right shift is precisely similar. The right shift operation moves the bit values of the number x by the number of bits y to the right, just like the last one, but in reverse direction. I just put the whole uncracked egg into the frying pan. Well, there you go. I don't think it's trivial. I would go to war against people who put cereal before milk. So wait, are you telling me when you eat cereal in the morning that you put the milk in the bowl first and then the cereal in? Because I do the opposite. I pour the milk over the cereal because that way you get at least some of the milk on every piece of cereal. You're wrong if you think you put milk in the bowl first. Oh, yeah. Okay. I avoid egg wars. I avoid eggs to not start wars. Anyway, I eat milk and cereal separately. Ooh, big brain. So, from a pragmatic standpoint, this is precisely the same as division by 2 to the power of y. No, it gets soggy. Okay. Then just eat it faster. Or get a type of cereal that doesn't get soggy. I really like the Harvest Crunch cereals because they tend to not get soggy as quickly. So, we have one final bitwise operator, which is one's complement. The one's complement operator, which is just the tilde, simply takes each bit and flips it. If you're the type of nerd that likes to squeeze either speed or power efficiency out of your code, bitwise operations typically take far less circuitry, and in some cases time, than algebraic operations. So, one question might be, like, why the heck would we need to ever use bitwise operations in like a non-embedded systems environment? Well, here's a thing that you may not have known about circuitry, right? The amount of power that it takes to perform a calculation, like the amount of electrical power that it takes to calculate something, is proportional, as one might expect, to the amount of circuitry that is used during that calculation, right? So, in certain applications, you actually do care about the power efficiency of your programs. One such example is in a server farm. So, in server farms, right, one of the major expenses of running a server farm, aside from the electrical power itself, is cooling, right? Huge air conditioning plants on server farms, because all they're doing is turning electrical power into heat, plus some sequence of ones and zeros. So if you have a program that's running on a server, in a server farm somewhere, and you can, even perform a very slight number of adjustments, like, for example, turning division. Division is usually a very expensive operation. If you can turn division into a right shift operation, or multiplication into a left shift operation, you save a small amount of power. A very small amount of power, but a small amount of power saved a small amount of power saved several hundreds of times per second, multiplied by 10,000 servers, that can actually have a pronounced effect, a noticeable effect on, your air conditioning bill for a server farm. But yeah, how is one's complement of x different from not x? Well, you don't have precisely a not x. So in C, it's exclamation point, and I don't know how it works, at the bit level. In this, with one's complement, you're guaranteed that every bit ends up as its complement. But I'm not sure if that's the case with not, or the not operator, because Well, think about it this way. It has to work with Boolean, right? So the way that Booleans are defined in C is that 0 is false and anything not 0 is true. So what the not operator the not operator has to still be able to deal with cases of like you know, like if not and complement were the same thing, then you would get like all ones if you said not false. But if you said not true, like true, if you had like the number 5, right? The ones complement of 5 would be would still be true, so it wouldn't work as a Boolean inverse operation. It has to be something more like if anything is 1, then 0 everything. And if it's all zeros, then set probably just the first bit to 1. It's typical to use 1 as true, but technically speaking, anything not 0 is valid as a true value. So, one other useful thing that you can, one thing that you can do with Bitwise operators, which is kind of interesting, is they can kind of be a minimal set of operators that you can compose other operations out of. So here are some common operations using Bitwise operators instead of using our regular arithmetic operators. So if you wanted to do a subtraction operation using only Bitwise arithmetic and our control flow and variables and whatnot, you would have the following. So you would define an integer that contained this integer is just for keeping track of what is borrowing from what. So while y is not equal to 0, borrow is equal to the complement of x ANDed with y. Let me see, do I do these? Yeah. I don't have like an illustration for this, just the code. X is then equal to x XOR with y, and y is borrow left shifted 1. Left shifted by 1. So if you repeat that until y is completely exhausted, then you're done. We could actually do this just to demonstrate that it works on a really small integer. So let's say that x is equal to 0, 0, 0, 0. Or actually, no, we'll do something more interesting than that. Let's say x is 1, 1, and y is 1, 0, 1. We then have borrow, right? So let's just call it b. Let's iterate our algorithm. B is initially equal to 0. If I were in a physical class, I would be doing this on the board. First, borrow is equal to the complement of x. So the complement of x is this. ANDed with y, so that is that. Good. Next, x is equal to x XOR y. So x XOR y, because that's only when they're different. So there we go. Oh, I should have like said what we're starting off with. So this one is 4 plus 8 is 12. This one is 4 plus 1 is 5. So complement or XOR, y is then equal to borrow left shifted by 1. So we take borrow, left shift it by 1. There we go. Good. We then set borrow equal to x complement with y. There we go. Borrow. X is equal to x XOR y. So that gives us that. We then left shift y by 1. borrow is equal to this inverted and y, so that stays like that. X, XOR y, that's all that, and y is right shifted. If you know what the answer is, you'll be yes. If you realized up here that the answer is 7, you should be excited right now because we're about to complete the calculation. So borrow is x inverted with it, which is all zeros. So all zeros and anything is still all zeros. X is equal to x, XOR y, so we can get rid of that. And y is equal to 0. That breaks the loop. So we then return x as our result. The result is 7. Ta-da-da-dum, da-da-da-bum-bum-bum. Ta-da. I'm so confused. What did I do? I just took these very short integers and I've been iterating the subtraction algorithm with them in Bitwise. So, just to demonstrate that it works, let's do the same thing, but with addition. Let's add that number to 0, 1, 1, 0. There we go. So this is 2, and this is 6. So, we're also going to need a carry register, initially filled out with zeros. So, while y is not equal to 0, carry is equal to x and y. So this is carry. Addition is a little more intuitive, straightforward to understand because the addition algorithm is basically the same. This is the same algorithm that you would have learned in grade school for adding numbers with multiple place values. Except it's in binary code. So x is equal to x, XOR y. So x is equal to this. Y is equal to carry moved forward by 1. So there you go. Now carry is equal to one and the other, x and y. X is equal to 0 because x is equal to x, XOR y, which is 0. Y is equal to carry moved forward by 1. There we go. Carry is equal to x and y, which is 0. X is equal to x, XOR y. There we go. Y is equal to now 0. So we return x, which is, of course, 8. Da-da-da-dum. So there you go, Bitwise. You can compose other operations out of this. Cool. So let's talk about 2's complement. Have you ever wondered how integers store negative numbers? The answer is in the title, 2's complement. Your computer interpreter. How does it work when it is x and y? X and y is just you go through each bit. If they're both 1, you take a 1, and if either is 0, you take a 0. Your computer interprets any integer with a leading 1 to be a negative number so long as the integer doesn't have the unsigned tag. So, if we were to take the maximum values of integers, right, interpret them as either a signed or an unsigned integer, this is what we get. So all f, which of course, if you remember your hexadecimal, f is 4 ones, right? So this is all ones. All ones is -1. All ones, if it's unsigned, is like this big long number. If you subtract 1 from this, you get -2. And if you subtract one more, -3, -4, etc., etc. And if you subtract one on each of these for the unsigned interpretation, you have the number going down as well. So, if you perform the 2's complement operation on a number, it flips the sign. First, you take the bitwise complement. Second, you add 1 to the number. Third, profit. So that's how you turn a number from signed into unsigned. Or from unsigned into signed, pardon me. The same procedure changes a negative number into a positive. So, for example, if we have, so in hexadecimal, if we have just A's, all A's, right, and then signed and unsigned interpretations of such, the unsigned interpretation of this number is, well, not particularly interesting to us. The signed interpretation is like 1,431,655,766. So, if you take the 1's complement of that value, if you take a look at the number A, right? You've got, this is 8, this is 9, this is A, right? If you invert the bits, you get 0101, which is, of course, 1 plus 4, which is equal to 5. So A flips and becomes 555555555. So if we do that, if we flip it, we turn this number into a positive number, but with it's 1 less. So you then have to add 1 at the end. And that is how you actually convert a positive number into a negative number at the level of bitwise operations. What is signed? Signed means that it includes a sign. So signed integers can be negative. Unsigned integers cannot be negative. They're only positive. So you can think of the unsigned integers as sort of mapping onto the natural numbers, including 0. 0 is a natural number, controversial opinions. And if you you can map signed arithmetic onto the integers proper. Like they're both called, like an unsigned integer technically is a natural number, but it's still called an integer, but for historical reasons. But yeah. Okay, but why does this work? Let's think about the addition operation. During decimal addition, we go through each pair of digits, starting with the least significant, and add the digits. If the result is greater than 1 digit, that result is added to the next place value. The procedure in binary is exactly the same. So, for example, if we wanted to add 21 and 19, we would add the 1 and the 9, we'd get 10, so we'd carry the 1, and then add those together and get 40. So, welcome back to elementary school math class. So, if you want to perform the same operation with binary, you do the exact same procedure. 0 plus 1 is 1. 1 plus 1 is 0. Carry the 1. 1 plus 1 is 0. Carry the 1. 1 plus 0 is 1. So 7 plus 2 equals 9. Consider the following. Let's try to add a negative number to a positive number, with the negative number being represented in 2's complement arithmetic. Right? So, if we have, so negative 14 is 11110010, and 25 is 000110001. So 0 plus O plus 1 is 1, 1 plus O is O plus O is O plus 1 is 1, 1 plus 1 is O, carry the 1, 1 plus 1 plus O is O, carry the 1. 1 plus 1 plus O is O. Carry the 1, etc. All the way to the end. And then we have one overhanging. Since the overflow digit is lost, this can be said to work. So remember, this isn't Python land. When your integer, or when your number, exceeds the bounds of what it's supposed to be able to hold, anything that overflows is lost, right? So, if you were to actually calculate this out, 0 plus 0, like, this binary number converts to 11, which of course is 25 minus 14, or negative 14 plus 25. So, there you go. You could put the following to a beat, and you'd have a nice rap. Yeah. I'll leave that as an exercise to the reader. So, that's, so, good. Any questions about that? Because otherwise, our next topic is like, and now for something completely different. We're going to talk about some, like, discrete math. We're going to get some discrete math in your bones. So, any Bitwise questions? What topics will A4 be on? I'm a bit wiser now. Excellent. I don't know what either of the poll options mean. Well, you remember how I was saying 1 is true and 0 is false? That's kind of what I was doing. I was trying to be clever. What topics will A4 be on? A4 primarily covers the material from topic 7. This should be topic 8. It's primarily the string manipulation stuff. I don't even I don't understand the adding and subtracting code using Bitwise. It's not necessary for you to, like, if you want to know, just try it out by hand. It's not necessarily necessary that you understand how the algorithm works, like why the algorithm works. Like, knowing that it works and that it only uses bitwise operations is sufficient for me to say, ha! Got you! It does work. Bitwise isn't useless. When do you carry the 1? You carry the 1 when this would result in 2, right? So the binary representation of 2 is 1, 0. You can't represent 2 in one binary digit, so you carry the 1 to the next place value, right? It works exactly the same as in, addition that you would do by hand. If the kids still do addition by hand. Well, maybe I should, like, make a math sheet for binary arithmetic, and, like, you guys, like, did you guys ever do, like, cram sheets? Or not cram sheets, what do they call them? Drill sheets. Did you ever do, like, math drills in elementary school? Please let them not have taken math drills from elementary school. That will make me so sad. So I'm out of time. Next time we'll do a brief introduction to graph theory, which is like a brief introduction to time by Stephen Hawking. Did you guys ever do math drill sheets? Because I kind of feel like it would be useful for you guys to have like a math drill sheet for these binary operations. Minute math. Yeah, there we go. Minute math. When I was in school, they called them math drills, but I was also like at the point in school where I was doing math drills, I was also doing them in Alberta because that's where I lived at the time with my parents, you know, because I was like a 6-year-old. But yeah, no, drill sheet. No, it's not homework. It's like the teacher would hand out the drill sheet. You'd have it'd be almost like a math quiz, except you didn't get, like, your marks didn't count, if that made sense. But it's like, here's too many math problems for you to be able to solve in 5 minutes. See how many of them you can do in 5 minutes, and that was the exercise. Ethan got Harvey's for doing it in less than 45 seconds once. That's awesome. That's awesome. Yeah. So yeah, it wasn't homework. It was an in-class activity. And then, like, you would, like, pass your sheets to the person next to you, and the teacher would put the answers up on the board, and you would mark the sheet, and then pass it back to the left, and then you'd see how many you got right or wrong. Because accuracy counts. It's not just how many you got done, it's how many you got done correctly. Yeah. That's the only way to really learn, like, arithmetic. That's the only real way to learn arithmetic, I think, is drill sheets. I got a slap for not finishing it in under 10 minutes. Well, depends on the number of questions, right? You know? But teachers shouldn't hit students. They're allowed to abuse them psychologically, but they're not allowed to abuse them physically, at least not in Canada. Will the solutions to the test and the assignments ever be posted? I'll have to think about that one. I need to, yeah, I'll take a look. I'll see what Chev has been giving you guys for feedback so far. Just kidding? Yeah, you're better at math than that. Come on. Okay. Well, if there's nothing further, I'll be logging off here. Will the test cases we used be posted so we can see what made our programs break? For legal purposes. Yeah, we'll see to it that you guys get some degree of feedback. I'll take a look at what you guys are currently getting for feedback. Take her easy. Have a nice one day. Go get yourselves a hot chocolate. I know it's still only 10:30 in the morning, but I feel like you've earned a hot chocolate. See ya.